In today's tutoring video series from Raritan Valley Community College, we'll be working on some problems from Chapter 1 about understanding units and conversions. So the next question we're going to be looking at is question 30 in Chapter 1, and it says that water is poured into a container that has a small leak. The mass m of the water is given as a function of time t by m of t is a function of 5 times t to the 0.8 power minus 3t plus 20, where m is in grams and t is in seconds. So the problem is asking us to find what time the water mass is the greatest, what is the greatest mass at that time, and then we want to find the rate of mass change at 2 points of time. So for the first question, we have the function m of t, which describes how the mass changes with time. And what we want to do with this equation is we want to maximize it and find the largest value. And the way we do that is by taking the derivative of the mass function and setting it equal to 0. So when we take the derivative of this function, the derivative of 5t to the 0.8 is going to be 5 times 0.8 t to the 1 to the 0.8 minus 1. The derivative of negative 3t will just be minus 3, and the derivative of 20 will be 0. So if we reduce all of our terms, 5 times 0.8 is equal to 4 t. 0.8 minus 1 is negative 0.2 minus 3. And the objective here is to figure out at what time t is this function equal to 0. Again, we're setting the derivative equal to 0 to optimize our function. In other words, this will find anywhere where the slope is equal to 0, which is any potential maximums or minimums of our graph. So in order to solve this for t, we have to add 3 to both sides. We want to divide both sides by 4. So we're going to have t to the minus 0.2 equals 3/4. And now we want t to be to the power of 1. So we have to raise everything to the 5th power, the negative 5th power, because negative 5 times negative 0.2 is 1. So we have t to the negative 5 times negative 0.2 equals 3/4 to the 5th power. To the negative 5th power. So this is equal to 4 to the 5th power over 3 to the 5th power. Because we have a negative here, we can take the reciprocal and remove the negative. So 4 to the 5th over 3 to the 5th is equal to 4.2 seconds. And so this is our potential maximum or minimum. We've optimized our function, but we have to make sure that our function is going to be finding a peak but it could also be finding a trough. And so we need to verify that the point that we found is indeed higher than the surrounding points. So first we want to find the mass at 4.2 seconds, and we do this by plugging in t of 4.2. So we have 5 times 4.2 to the 0.8 minus 3 times 4.2 plus 20. And the mass at t equals 4.2 seconds is equal to 23.160 grams. So now we know the mass at 4.2 seconds. We want to test to see if the mass at 4.2 is greater than the mass at 4 seconds. And we want to check if it's greater than the mass at 3 seconds. If both of these hold true, then we know this is a maximum because the point 4.2 is higher than both of its surrounding neighbors. So plugging in the mass of 4, the t equals 4 to our mass equation, we'll see that we get 23.15 grams. And solving for t equals 3 is equal to 23.04 grams. And so both of these statements hold true. So that confirms that the greatest mass occurs at t equals 4.2 seconds. In solving this problem, we also determined part B, what is that greatest mass, when we found m of 4.2. So the mass at the time when the water has the greatest mass is 23.16 grams. So now for the next part, in kilograms per minute, what is the rate of mass change at C, t equals 2 seconds, and D, t equals 5 seconds? So in order to do this, we want to take our derivative which we found before to be 4t to the negative 0.2 minus 3. So now we want to find the rate of mass change at t equals 2. So we're going to set t equal to 2 in the derivative of our mass equation. So when we do that, it's going to look like 4 times 2 to the negative 0.2 minus 3. Solving this algebra results in a mass change of 4.82, and since the problem tells us that m is in grams and t is in seconds, the units of the derivative of the mass function is going to be in grams per second because we've divided by time, divided by a change in time. So we want to convert this number into kilograms per minute, which is the unit that they're asking for. So we know that there is 1 kilogram equaling 1,000 grams. So we use the first conversion factor, 1 kilogram over 1,000 grams. And we know that there is 60 seconds in 1 minute. So our second conversion factor is 60 seconds over 1 minute. Multiplying all of these numbers out, we will cancel out the units of grams, and we will cancel out the units of seconds, leaving us with only kilograms per minute. And the numeric answer for this is 0.289 kilograms per minute. Additionally, they ask us to find the mass change at t equals 5 seconds. So again, we take our derivative, and we solve it for t equals 5. And evaluating this for t equals 5 gives us a result of 0.10088 grams per second. Now again, we must convert this into kilograms per minute. So using the same conversion factors as previously, we have 1 kilogram equals 1,000 grams times 60 seconds over 1 minute. And the result of this is negative 0.00605 kilograms per minute. And so the reason this is negative is because at t equals 5, the water is actually draining out of the bucket faster than it is being poured into the container. And so as a last step, it might be beneficial to express this number in scientific notation. We would do this as such. So that is the final answer, and we have solved all of the parts of this question. So that's it for this video series. Please join in for the next one.